Okay, we're back. Let's continue with working the rest of these review problems from derivatives. This one we're going to find the second derivative of sine of 2x. Of course, along the way we'll have to find the first derivative. So the derivative of sine of 2x, we basically make the substitution u is 2x, so du over dx is 2. Let me fix that real fast. So the derivative of sine of u is what we're trying to find. The derivative of sine of u is cosine of u times the derivative of u. So that's just 2. That's just cosine of 2x. So the first derivative is 2 cosine of 2x, which I've checked here using the calculator method. The way you can check this on a TI-84 is you put the original function, sine of 2x, in for y1, put the numerical derivative of y1 with respect to x, evaluate an arbitrary x and sine in y2, and put your answer, 2 cosine of 2x in y3. The tables for y2 and y3 should match, which they do, as you see here. The second derivative of the original function then is the derivative of the derivative of the first derivative. So the derivative of the second derivative of sine of 2x is the first derivative of 2 cosine of 2x, that is 2 cosine of u. So constant multiple rule says you just bring the 2 out front. The derivative of cosine of u is minus sine of u, so it's minus 2 sine of u, but then times the derivative of the u because of the chain rule there. That derivative of the u is 2 times that negative 2 is negative 4 sine of 2x. So the second derivative, which is what we were looking for, is negative 4 sine of 2x. And I can check that by doing the, since I've already checked that the first derivative is right, then I put the first derivative in for y1 and the second derivative in for y3, leave y2 alone, and y2 and y3 should now match once again. Here are the graphs of all of these functions. The original function is in blue, the derivative is in red, the first derivative, and the second derivative is in green. And you can study that a little bit to see that all the correct relationships are going to hold. Like, for example, when the first derivative is 0, here, here, and here, we have a maximum or a minimum on the original function. When the second derivative is 0, here, and here, and here, which is really the same places that the first original function are 0, those are the inflection points. And so forth. Things like when the original, let's see, when the derivative is positive here, the original function is increasing. When the when the derivative is negative, like say in here, the original function is decreasing. When the second derivative is positive, like across this part, the original function is concave up, and so forth. Here we have y equals 3x cubed minus 4 square root of x plus 5 over 2x squared. Find the first and second derivatives. Well, the trick here is just to rewrite this as a sum of power functions, and it's pretty easy. The square root of x is just another way of writing x to the 1/2 power. And we can rewrite this as 5/2 times x to the negative 2. So taking the derivative there, which would be dy over dx, you just use the simple rule, take the power times the coefficient and subtract 1 from the power. So that first term becomes 9x squared. The derivative of the second term, 1/2 times negative 4 is negative 2. 1/2 minus 1 is negative 1/2. And then negative 2 times here that cancels the 2's, and you get negative 5, and the power goes down to negative 3. Now that would be a perfectly legit way to write the final answer of the problem, except that the original was given in this form. So let's change it back to the similar form. 9x squared is fine, but I'm going to write this as negative 2 over x to the 1/2. X to the 1/2 is the square root of x. So this is negative 2 over square root of x. And this is negative 5 over x cubed. But I'm going to use the middle version to take the next derivative. So for the second derivative, I'm doing the derivative of the first derivative in this middle form here, sum of power functions. So 2 times 9 is 18x. Negative 1/2 times negative 2 is positive 1, and the power goes down to negative 3/2. Negative 1/2 minus 1 is negative 3/2. And negative 3 times negative 5 is positive 15, and the power goes down 1 to negative 4. Again, that's a legitimate way to write it, but let's rewrite it in a form similar to the original function. So the second derivative is 18x plus 1 over x to the 3 halves. 3 halves is 1 and 1/2 in mixed number form. So that would be an x and a square root of x there, multiplied together. And here we have the last term is just 15 over x to the 4th. And here are the checks, checking them like we did the ones earlier. You can pause that and take a look at and see that they do check out. Here are the graphs. The original function is in blue, the first derivative is in red, and the second derivative is in green. Notice that the first derivative is 0 only one time at one place there, and that's where the original function has a minimum. The first derivative is increasing everywhere, so the second derivative is always positive, and the original function is always concave up. All right, how about this one? G of x equals 3 times x to the 2x power. The 2x power is on the x. Find the first derivative, evaluate at 3. So g of x is 3 u to the v, where u is x and v is 2x. So this is going to be a generalized power exponential rule problem. Okay, the derivative of the u with respect to x is 1, the derivative of v with respect to x is 2. So what you do is you first, well actually I just pulled the 3 out front, and then you treat it as a power rule first, v times u to the v minus 1 times the derivative of u, plus you treat it as an exponential rule, natural log of u times the original function u to the v times the derivative of v. Okay, so just substitute back in. V is 2x, u is x, and then this is 2x minus 1 for the power. That derivative of u is 1. Over here we have log of u is x, and this is x to the 2x, and then that derivative is 2. So let's see, they both have a 2 here. So I'm going to factor that out, times the 3 is a 6. Okay, if I multiply that x by this one, that power goes to be x to the 2x. And then we have an x to the 2x here, so I can factor that out front. And what's left, well, nothing's left here because all of this was canceled out. In other words, if you take all of this and multiply it together by 3, you'll get 6x to the 2x. So that just leaves a 1 there, plus, and this is just log of x, natural logarithm of x. So that final answer for the derivative g prime of x is 6x to the power 2x times parentheses 1 plus natural log of x, close parentheses. We evaluate that at 3. We just plug in 3's everywhere we have. Look at the power first. 2 times 3 is 6. Then we have 3 to the 6th times 6, which is supposed to be, I guess it's 4,374. I worked that out with a calculator somewhere. And then you can't really simplify this other part any. It's just 1 plus natural log of 3. If you put in a calculator, you get approximately 9,179.33. And if I did the numerical derivative, that's basically what I get. It's at least agrees to tenths place to 5 significant digits. With a smaller h, we could get it to agree more closely, I bet. But checking that out here with the derivative, it seems to check out fine with the formula here. We're only going to define this for positive x's, so we're going to see that here, and the blue is the original and the red is the derivative there. But it's like the blue has one minimum because the derivative is going to cross the x-axis one time. The derivative is always increasing, so the original is always concave up. So if we did a second derivative, it would always be positive. Continuing on, h of x equals e to the 5x squared. 5x squared is the power. find the first derivative and second derivative, and maybe evaluate those both at 0. Okay. So h of x is 5x, e to the u basically, where u is 5x squared. That makes du over dx 10x. So the derivative of e to the u is e to the u times the derivative of the u. So that's 10x times e to the 5x squared. And if you plug in x is 0, this is e to the 0 is 1, but then the 0 here makes it 0 overall. Okay, and if we do another derivative, we've got the 10 we can factor out front. And then we have the product rule, x times the derivative of e to the u. Let's see here. I think I want to say that x first times derivative of the second plus the second times derivative of the first. Derivative of the x is just 1. The derivative of e to the u is e to the u, and we already saw the du was 10x. So let's see what we have here. This is 10x squared plus 1, where we factor out the e to the u in the, well, I did in the back side here, but I could have put it in the front. I don't know. And so we get that. Let's see. So it's 10 times 10x squared plus 1 times e to the 5x squared. If we evaluate that at 0, it's 10. Let's see. Put in 0 here. 0 squared is 0 times 5 is 0. E to the 0 is 1. So it's 1 for the last part. 0 squared is 0 times 10 is 0 plus 1 is 1. 10 times 1 times 1 is 10. So the second derivative at 0 is 10. So we should see so here are some calculator checks here on the right. This is a TI-84 checking that. Here's checking the first derivative and the second derivative. There's the second derivative is 10 there as well. That's another check. And the graphs, here they are with the correct graphs here. The blue is the original f of x, e to the 5x squared. The first derivative is right here, showing a minimum on the original function at the origin. I mean, not at origin, but when x equals 0 and y is 1. And that's when the first derivative is 0. And the second derivative is 0. The second derivative evaluated at 0 is 10. The second derivative is never 0. It's always positive, meaning the first derivative is always increasing, and the original function is always concave up. Okay, a couple more to go here. How about a rational function? To use the quotient rule here a little bit. And we're going to analyze this function a little bit. So this one here, I'm going to factor this out. The bottom is x minus 5 times x plus 2. You can check that with FOIL, and it works out. And let's see, we might graph it first, right off the bat, if we have graphing technology. Okay, and we might see that it looks like the original crosses at, looks like maybe at 2. Or maybe at -2, we might have some canceling here. So one thing we might look for is if there's any canceling. So we might try to see if x plus 2 is a factor. So let's go ahead and put that in there. We're going to divide by x plus 2. Do some long division here. 6x cubed divided by x is 6x squared. It should be kind of lined up over the x squares there. 6x squared times x plus 2 is 6x cubed plus 12x squared. Then change the signs and add, cancels that out. Gives us a -5x squared plus these other terms. -5x squared divided by x is -5x. This gives us, multiplied out, gives us negative 5x squared minus 10x. Change the signs and adds, cancels that out, gives us negative 6x minus 12. Negative 6x divided by x is negative 6. Multiplied by this gives us negative 6x minus 12. Change the signs and add. Since that is a zero remainder, that says that this top factors as x plus 2 times the 6x squared minus 5x minus 6, which we can use anti-FOIL type factoring to get that to be 2x minus 3 times 3x plus 2. So this cancels the x plus 2's as long as x is not negative 2. Or we can leave the top, like this. Another way we could do it is actually divide the bottom into the top, long division, something similar to what I did here. I don't think I have the details written out on that, but if you do that, you get 6x plus 25 plus a remainder of 119 over x minus 5. I actually did this version, divided out. So very similar to what I did here. Just take the 6x squared minus 5x minus 6 divided by x minus 5. And we see we get a linear function, 6x plus 25 plus this remainder, 19 over x minus 5, which says this y equals 6x plus 25 is going to be a slanted or oblique asymptote. That's this maroon dotted line here is our oblique or slant asymptote of the original function there. Okay, which among other things means that this function is going to have the same end behavior as that. More or less the same end behavior is just 6x cubed over x squared, which is 6x. So it's going to have a line of slope 6. More specifically, 6x plus 25 is its asymptote. So it goes off to infinity on the right and negative infinity on the left. But we have an asymptote there. Notice that the original function is going to have a hole in the graph whenever x is negative 2. If you put negative 2 in this expression here, you'll get the y coordinate of that hole. I think I'll do that in a minute. And then it turns out that all of the derivatives are going to have holes at x equals negative 2 as well. First derivative, second derivative. We have an asymptote, a vertical one, at x equals 5 on the original function. And the derivatives will also be undefined there and have that. So if we plug in negative 2 here, let's see, did I work that out? I don't have it worked out here, so let's just talk through it here. Negative 2 plugged in the bottom is negative 7. In the top, negative 2 squared is 4 times 6 is 24. And then this is minus 6 more is negative 30. And then a negative 2 times 5 is 10. So it's negative 20 over, let me think about this. Did I do this right? 24 plus 10 is 34. 34 and then minus 6. 34 minus 6 is 28. 28 divided by negative 7 is negative 4. Okay, so that says that negative 2, negative 4 is the limit point. It's a hole in the graph. So we should see that on the graph right there. Hole in the graph. All right, going back up here. All right, now let's find some derivatives. So we're going to use the reduced version to find the derivative. Okay, so we got a little quotient rule going here. So the bottom times the root of the top minus the top times the root of the bottom over the bottom square. This derivative right here is 12x minus 5. This one is just 1. Distribute FOIL, distribute the 1 here. So this is 12x squared plus 25. We got a negative 60x minus 5 more x's and negative 65x. All these things change sign like that. We still got the x minus 5 squared. Leave it factored in the bottom. Combine like terms in the top. We got 6x squared minus 60x plus 31. all over x minus 5 squared. Notice again, 5 is a vertical asymptote. We also still need this restriction that x is not negative 2, so this does have a hole in it when x is negative 2 as well. You could do it without simplifying first, but it just is a little harder. I'm not going to talk you through all the steps there, but it's the same steps. It's just the factoring of this thing right here, this 4th degree polynomial, is a little nasty at the end. But it turns out that all the x plus 2's end up canceling out. You get the same thing, it's just a little harder. When is the first derivative equal to 0? Well, it's 0 when the top is 0 and the bottom's not. Well, we just want to find when the top is equal to 0 there. So that's basically a quadratic formula problem, which I work out here. And it's 5 plus or minus square root of 714 over 6. Okay. So the first derivative is positive, and the original function is increasing from negative infinity to the 5 minus the square root of 714 over 6. And then it's also increasing from 5 plus the square root of 714 over 6 to infinity. And the first derivative is negative in the middle part between those two places. And of course, it's 0. First derivative is 0 at these two x values. And there's the corresponding y's. I'll leave it to you to work the details out of that. It's just plugging in, but you have to be a little careful with the square roots there. And those are the local extreme of this one here turns out to be a maximum and a minimum over here. The second derivative, we want to take the derivative of that first derivative. So then we do a similar thing, the quotient rule, bottom times root of the top minus top times root of the bottom. This one is not too bad, 12x minus 60. This one is u squared, so it's 2u, and then times the root of the u is 1. And so we have to square this out. Let's see, actually what I did is I noticed I both had an x minus 5, and I both had a 2 here, and I can factor 2 out of that. So I have the other x minus 5, factor 2 out of that is 6x minus 30. And then this one is just then negative 1 times this quadratic. So that makes this a little bit nicer. Oh, what did I do here? I just canceled one of the x minus 5's. Okay. And it's pretty typical of these pattern I've noticed before when you do a rational function like this. If it has a power on a factor in the bottom, that's going to actually end up going up by just 1 in the bottom in the end, because you're going to get some canceling. It's a typical thing that happens. So anyway, where are we here? We've canceled that out. So now we're just going to go ahead and multiply these out with FOIL. That's right here. Distribute the negative 1 here. Combine like terms, and the 6x squares cancel, and so do the 60x's. So that kind of is nice because we just have a constant then in the top of ultimately 238 over x minus 5 cubed. So that's just a transform power function there. Again, we need to put the restriction that x is not equal to negative 2 really all the way down. And that's equal to 0 never. So the second derivative is never negative, never 0. And the second derivative so it's either, well, actually it's never 0, but it's negative whenever the x minus 5 is negative. So when x is less than 5, the second derivative is negative and the original function is concave down. And when x is bigger than 5, then we have the second derivative is positive and the original function is concave up. So we should see that here. Let's see. So here's your 5. X equals 5 is your vertical asymptote. The first derivative is, well, the original function is the blue one here. It has a minimum in here somewhere where the first derivative is 0, somewhere in this vicinity. The second derivative is positive there, so the original function is concave up, and the first derivative is increasing. They all have holes in them. It's not indicated here, but they're all have holes here when x is -2. And you can see the one for the original function. And here we have the, again, the first derivative. The original function is blue, the first derivative is red, and the second derivative is green. I think we just have one more. Let's go ahead and knock this out. Compute the derivative of the arctangent or inverse tangent of x to the fourth. And let's substitute u as x to the fourth. Then du over dx is 4x cubed. The derivative of arctangent of u is 1 over u squared plus 1 times the derivative of the u. So u is x to the fourth, so plug that in, square the x to the fourth, you get x to the eighth. And then this is the 4x cubed here, so that can go up to the numerator. So we have ultimately 4x cubed over x to the eighth plus 1. Once again, here's the check in the calculator. Everything seems to be checking out nicely. There's the graph of the original function in blue and the derivative in red. Notice that the derivative is 0 only one time when x is 0. And that's when we're going to have a local minimum, actually a global minimum as well, for the original function. And when x is 0, the original function is also 0. 0 to the fourth is 0. The arctangent of 0 is 0. So the original function goes through the origin, and that's a minimum. You might notice something also that's interesting. The original function is actually an even function. If you take, because of the fourth power here, makes that have an even function, so it has y-axis symmetry, which means its derivative is going to be an odd function. It has origin symmetry, which you can see here as well. The original function does have one minimum and no maximum. You may also see that the original function, the derivative, has a maximum there and a minimum here. So the second derivative will be 0 there, and that will be the places where the inflection points occur. The x values, of course, will be the x values of the inflection points on the original curve. Another thing that's interesting is we do have a horizontal asymptote in both cases. So it's pretty easy to see that the horizontal asymptote is 0 for the derivative, so that means the derivative is going to be coming into approaching the x-axis asymptotically. But what about this one for the arctangent? Well, if we take the limit as x goes to infinity, then u is also going to infinity. And arctangent has an asymptote of pi over 2. So this is pi over 2 here, and it's the same on both ends. All right, well, I think that gives us a pretty good review of some different derivative functions. Obviously, I didn't go over every single possible derivative thing, but if you can do these, you're probably on your way towards being ready to be able to do a test over some derivatives.